Interstate I-20 connecting to I-59 in downtown Birmingham is a busy corridor in the city's central business district. When the time came to rebuild and replace the nearly 8 miles of old bridges with new bridges, the Alabama Department of Transportation knew they faced a major challenge. The construction process had to be precise and efficient, causing as few construction delays as possible. For these reasons, the Alabama Department of Transportation used state-of-the-art 3D design and construction analysis to identify critical issues and potential construction delays before the project broke ground. This section of I-20 was originally designed and constructed in the 1960s to last 30 years and carry a maximum of 80,000 vehicles per day. But by 2010, the Birmingham-Hoover metro area had grown to a population of almost 1.1 million people, and the corridor was carrying 160,000 vehicles per day, twice the number it was designed for. Over the past decade, many of the bridges in Birmingham's central business district had begun showing their age. Sections of concrete were falling off the underside due to constant use, and some areas under the bridges had to be fenced off in order to protect pedestrians. Plans began to construct a new corridor and close the critical section of I-20 for 11 months, rerouting all east-west traffic around the south side of town on I-459. In order to minimize the disruption to traffic in this heavily developed area, the Alabama Department of Transportation leveraged 3D technology to analyze the new and existing design of the complicated system of surface roads, bridges, and interchanges. This revolutionary technology, used on similar projects in other states, is known as BIM, or Building Information Modeling, and identifies potential construction delays, ultimately reducing unknown construction change orders and saving time and money on the project. First, a live computer model was built of all existing structures above and below ground located in the new transportation corridor. Then, a computer model of the new proposed design was virtually created from the proposed design drawings. Anywhere an object in the existing model touched an object in the new model, a clash was detected, and a report generated for designers and contractors to address before construction began, avoiding costly reworks and delays. The first step in the process was to collect all of the existing survey and mapping data files to document the existing conditions. These files included LiDAR helicopter surface data, aerial fixed-wing LiDAR data, terrestrial laser scanning data, and even downtown Birmingham Geographic Information System data. All of these datasets were merged into one large file. Bit by bit, all of the elements, including the underground utilities, were turned into a full 3D model of the existing conditions. When all of the underground utilities were put together, this is how the 3D model looked. The next step was to build a model of the new proposed road and bridge design. This was done by the Alabama Department of Transportation Visualization Group. Using the proposed design drawing, they converted the 2D drawings into the 3D models seen here. Both models were compared, and everywhere the old model touched the new model, a clash was noted and a report generated. It was these reports that identified and documented where design and construction interferences would occur before construction began. The Alabama Department of Transportation understood that this process would not only save time by eliminating unknown construction delays, but also save money, because the final design would take into account hundreds of interferences that could lead to costly field fixes and contractor change orders. A leading virtual 3D modeling company, LandAir Surveying, created the existing structures and utilities models from the laser scanning data. The ALDOT Visualization Group, with the help of ALDOT engineers and consultants, converted the 2D design drawings and constructed virtual 3D models with geospatial precision. Their outstanding work was critical to the successful outcome of the project. Once both datasets had been inserted into the virtual environment, the clash analysis was performed. This example of one bridge segment shows that there were 73 solid interferences and 130 areas where the existing construction area contained interferences that would make construction difficult and create potential delays. These areas will be identified and studied to confirm that the interference is removed. Finally, a detail of the exact clash is shown, so that engineers have a visual of the interference. In this case, a proposed concrete footing would interfere with a communication cable in the same location. This is considered a hard clash that had to be addressed. The Mitchell Interchange project in Wisconsin was similar in size to the corridor project in Birmingham. In their study, The Federal Highway Administration and Wisconsin Department of Transportation estimated that approximately $9.5 million could have been saved on the Mitchell Interchange project if 3D modeling and clash analysis had been used during the planning stages. According to Autodesk, on average, 3D modeling and clash analysis costs just 0.2% of the total program budget, yet can save an average of 5.5%. The resulting savings of using building information modeling on a program over traditional methods can result in a return of about 20 times the original investment. On the Birmingham CBD project, 3D BIM analysis identified over 1,100 potential construction and design clashes. These are simulated photo matches provided by the Alabama Department of Transportation Visualization Group that show the proposed future construction. These visualizations were very helpful in public meetings and Birmingham City official meetings to help understand the public scope of the project, rather than looking at typical engineering drawings. The engineering world is embracing 3D BIM spatial analysis in every sector of design. Alabama's Department of Transportation is an early adopter. More and more transportation engineers and contractors are beginning to understand the cost benefits this revolutionary technology can bring to their projects.